Hello, everyone, and thanks for joining today's webinar. My name is Priya, and I'm the marketing lead here at VTEX. We are based out of New Jersey and provide optical transceivers and fiber optic solutions to telecom and data center industries. Quick note, this webinar is being recorded and the recording will be up on our website tomorrow. I'll be dropping a link to the webpage in the chat box shortly. For today's session, we are pleased to have Dr. Son of Optimind. Optimind has been doing a lot of work on non-DSP AOCs, working with OpenEye MSA. VTEX is a sales and business development partner of Optimind. Today, Dr. Son will share a progress update on analog CDR-based 400G AOCs. He's currently the CTO and CMO at Optimind. Dr. Son invented and developed a unique optical engine platform based on self-aligned optical assembly at Optimind. He has a PhD in electrical engineering from KAIST and holds over 40 patents related to optical interconnects. Dr. Son's presentation will be about 20 minutes or so. Please feel free to ask your questions by typing them in the Q&A box. And now over to Dr. Son.
Thank you, Priya. Good afternoon. Thank you for everybody to join VTEX webinar today. My name is Young Son, the CTO and CMO at Optimind Inc. I'm so delighted to share our recent progress on CDR-based 400G AOC along with PAM4 SR optics and introduction of first-in-class 400G QSFP 56DD AOC available at the market. In my view, architectural paradigm shift is required for 400G and beyond in data center. Today, switch in data center moves at higher speed from 100G towards 400G. The number of ports in a switch is increased to support more servers to save rack space and future expansion. The location of the switch will be changed from top of rack to mid of row or end of row to make layout of the rack more flexible. The AC could not cover mid of row or end of row reach for 400 gigabps data rate. VCSEL SR optics and AOC will replace copper DAC over 10 meter with multimode fiber link. The market volume requires high-scale manufacturing of AOC and SR optics module to meet supply chain management without shortage of the product. We should consider complexity of multiple parameters in designing VCSEL-based optical link in PAM4. Multimode high-speed VCSEL has various beam profiles, including beam divergence and spatial mode distribution. Optics design requires to receive all the beams from the VCSEL to transmit high-quality PAM4 signal to receiver. Direct modulation of VCSEL for PAM4 signal requires maintaining linearity for the operating temperature range. PAM4 optical signal performance is influenced by various parameters, including RIN, spatial mode partitioning noise, optical feedback, and crosstalk. We should consider how these parameters can be minimized in optics design. PAM4 signal level is 1/3 of NRG in principle, or even smaller than that, due to zeta noise, and signal can be affected by small amount of noise. Optical signal of PAM4 should be better than that of NRG in this regard for a wide range of VCSEL driving, and which requires very good optical coupling to fiber from the VCSEL. To get excellent optical coupling, we are using single die VCSEL and PD rather than an array. We could get maximum optical coupling for our channels by tuning up die position individually for multi-channel coupling of optical fibers like QSFDD or more. We defined the optimum channel spacing to get lower crosstalk between channels and larger lens diameter to achieve more alignment tolerance of optics. We got very unique optical engine with our own optics design. Using individual VCSEL and PD, we achieved desirable features from the design for the following. Lower optical crosstalk between channels, which can make lower optical noise from adjacent channel. We could optimize optical coupling for all channels and get stable optical coupling for wide range of temperature. Bigger lens diameter can make better quality beam and smaller spot size with a lower numerical aperture at fiber facet. Then we could get longer transmission with standard OM3 fiber by lowering the modal dispersion. Our design of optics does not use ferro as an optical connecting part, and it will bring higher productivity during the assembly. Two lenses are used to separate collimated beam optics to improve the optical tolerance for alignment. Wide beam aperture is attained by using an individual device instead of an array device. The air gap is eliminated to produce a lower reflection. Each optical device is mounted to its optimal position to ensure optimal optical coupling. The fiber guide structure can align A fibers passively without ferro. Our direct plug-in fiber modular coupling method for high volume optical assembly does not require any high precision alignment equipment owing to the self-aligned assembly architecture, which renders a fully passive self-alignment. We have achieved remarkable alignment tolerance with the smart optomechanical engineering. We implemented 400G QSFP56 DD-AOC with 2 units of 8-channel OSA and analog CDR-based chipset. This picture shows our optical coupling assembly process with custom ribbonizing. We devised a jig and fixture to make custom fiber spacing as a ribbon, and it is used to get easy optical coupling assembly with our own optical coupling station as shown. We could make optical assembly of QSFP AOC in a couple of minutes, including fixing fibers. As you see in the picture, optical power received at the PD for all 8 channels are very uniform among them. Let me show PAM4 optical signal, optical eye signal taken from conventional OSA with an NRG-based product and our new OSA for PAM4. As we identified with our own measurement, it is very difficult to make good PAM4 optical signal using a conventional OSA and could not get a good PAM4 output signal at receiver with an analog CDR chipset. DSP chipset can improve PAM4 output signal integrity significantly, but it requires additional latency, higher power to drive, and higher material cost as a return. Optomine achieved excellent progress with 400G PAM4 AOC up to 100 meter using OM3 fiber. We have obtained significantly stable optical eyes of PAM4 from our OSA and optical assembly operating at different temperatures. We do not use equalization for optical eye measurement. Optical eyes for all channels are similar to each other. Here is a snapshot of typical BR and burst error margin with 400G AOC working at room temperature. Maximum pre-FEC BR is in the range of 10 to the minus 10th, and maximum burst code word symbol error is 2 to 3. We could get several error-free channels, as you could see in the picture. We measured pre-FEC BR and burst error codes for 400G QSFP-DD AOC at 65 degrees C, the case temperature. The maximum pre-FEC BR was 10 to the minus 10th. We got an error-free condition for more than half of the channels. The maximum burst error code was just 1 at 65 degrees C. We measured pre-FEC BR and burst error at 70 degrees C for 1 hour, and the result shows very stable and still low BR and burst error. The maximum burst error code was just 2 at 70 degrees C for 1 hour. We measured BR and burst error codes for 400G QSFP-DD AOC at 70 degrees C for 12 hours. The maximum BR was still 10 to the minus 10th. The maximum burst error code was 5 for one channel and 2 for the remaining 7 channels. We measured the BR and the burst error codes for 200G QSFP 56 AOC with 100 meter OM4 fibers at 70 degrees C. The maximum BR was 10 to the minus 9th, and the maximum burst error code was 6. We implemented a 400G AOC with a 70 meter OM3 fiber and measured BR and burst error for 1 hour. The maximum BR was 10 to the minus 9th, and the maximum burst error code was limited to 3 only. We measured pre-FEC BR and burst error for a full range of operating temperature with 400G QSFP-DD AOC. The measurement started at minus 5 degrees C of the case temperature by turning on the power and continued to reach at 75 degrees C. We accumulated BR and burst error for a whole period of measurement for about 17 minutes. There was no problem to turn on power at cold start condition at an environment of minus 10 degrees C chamber. As you could see, RSSI values for all 8 channels moved similarly together along with the full temperature range from 5 to 85 degrees C of MCU. That means optical coupling for all 8 channels should be stable for a wide range of temperature. We measured pre-FEC BR and burst error for MCU temperature from 0 to 85 degrees C with 200G QSFP AOC. There was no significant degradation of pre-FEC BR and burst error count during the measurement. We maintained the measurement for 30 minutes at 85 degrees C to see any significant change of behavior of RSSI at highest working temperature, but the result showed very stable curve for all 4 channels. That means implemented OSA has a very good immunity in summary expansion for full range of operating temperature. I would like to announce our QSFP56DD 400G PAM4 AOC as first-in-class DSP-free product with a very good performance as shown in the presentation. We could make it as the game changer in PAM4 SR optics using analog CDR chipset solution. We achieved more than 3 benefits, including lower latency for HPC application and AI-based high-end server, lower power consumption for operating cost savings, and great production efficiency with a higher yield. We are one of founding members of OpenEye MSA that pursue analog CDR-based approach to get PAM4 solution product. Here is a list of optimized benefit in PAM4 AOC. We are using typical 28 gigabps pixel as a light source and our own designed and implemented OSA, which is our core competence. We do not use any ferro-type component to attach fibers to OSA, and so we use bulk optical fiber cable and cut and ribbonize during the assembly, which does not require predefined length of the cable. We do not need any heavy capital invested high precision alignment equipment during optical assembly, and we could ramp up the manufacturing capacity very quickly without blackout due to long delivery of the equipment. We could take advantage of lower latency and lower power consumption owing to use of analog CDR chipset. Let me show you one example calculation table on the cost savings in data center operation based on lower power consumption of AOC. Actual amount of cost savings shall be different from the table, and it is shown for your visual information purpose only. The calculation does not include additional cost savings for system cooling and power supply. We tried the link testing of 400G QSFP DD-AOC with a commercial 400G switch. We obtained a link up for all 32 ports without any problem. The maximum pre-FEC BR for the worst channel was in 10 to the minus 9th range. There was no FEC uncorrected code word for all 32 ports. Here is a roadmap for the first-in-class PAM4 AOC based on analog CDR solution. We have launched a pilot production since this October and started providing small volume of product as well as customer sampling of 200G, 400G AOCs and their breakout. We implemented advanced optical interconnect solution using our proprietary optical engine platform based on the patented direct fiber plug-in optical coupling technology. We apply the same technology to AOC, cable attached transceiver, and conventional transceivers. Our integrated optics and optomechanical structure of OSA and optical assembly algorithm improved optical performance, including optical coupling efficiency, minimal reflection noise, and higher production yield for volume manufacturing. Here is our current product spectrum for data center applications. We have PAM4 AOC solutions as a flagship product, including QSFP DD, QSFP, SFP, OSFP, and their breakouts with a flexible combination of each form factor. We are doing the same with 25 gigabps NRG products for both AOC and transceivers. Our transceiver can reach longer than standard SR specification with OM3 fiber, and cable attached transceivers are attractive to highly dense and complex routing of end of row or mid of row application with a patch panel deployment. In nutshell summaries, I would like to emphasize the following. We designed and implemented SR optics to meet PAM4 optical specifications using analog CDR. The following are the key features about our optics design. Our new optical engine has demonstrated an excellent AOC performance in PAM4 56 gigabps as a result. Optomine is ready to support high-performance computing, AI server, and hyperscale data center applications with its PAM4 AOCs. The next step for Optomine will be testing the optical engine with SR4 and SR8 modules for optical transceivers, and the product will be available in Q1 next year. If you have any question or inquiry, please contact me anytime. Thank you for your attention.
Thank you, Dr. Son. I think we have some questions. First question is, can you comment on auto CTLE timing? Do you have a DFE equalization in your analog CDR?
No.
So the next question is about 400G. You show 400G transceiver with 400 GAWI 8 on the host side, thus 8 lanes of optical needed. When do you expect 400 GAWI 4 to be implemented, which requires twice the speed of VCSEL?
Well, we have some longer-term roadmap on that 100 gigabps PAM4 solution. Sometime, probably end of next Q2 next year, or sometime third quarter next year, we may show the initial prototype of that product.
Okay, another question is the availability. I think it's a sample availability. When is the general availability date?
General availability for QSFP 56 and QSFP DD is already available. If you request any samples for evaluation, we can provide the samples right away. And also some small amount of sample order, like 10s and 20s, we can deliver it within 2 weeks after getting PO.
Okay, great. One more question is, how about the interoperability with DSP-based transceivers? Can you comment on that?
Yeah, we just tried with just one, the advanced product using DSP, and there is no problem to connect with that DSP-based transceiver with ours.
Okay, I think we have one more question. Just what kind of equalization do you have in your analog CDR?
I do not know in detail about that. So if you ask it in written, then I will get back to you from the support of our engineering.
Yep, okay, there's a couple more. How is the performance in terms of BER and symbol errors when you initialize at the low corner, -5 or 0 degrees Celsius, to the high corner or vice versa?
As I already shown in the presentation, there is almost no significant degradation at both lowest and highest temperature. Still maintain 10 to the minus 10 or worst case -9 BR. And also the code word symbol error is limited to 5.
Okay, I hope that answered the question. I think there is it 8 channel for TX or 8 channel for RX?
Yes, for the QSFP-DD, right.
Yeah. Okay. So if you have any further questions or would like to request a sample, please email us info@vtextech.com.